Okay, let's dive into this. Picture this for a second. You've just spent hours mashing grain. You've carefully separated all that sweet liquid from the husks. And now you are holding hundreds of liters of raw, unstable, and quite frankly, micro-brittled liquid. What you do in the next 60 minutes decides absolutely everything. We are looking at wort boiling today, and when I first looked at the data on this, one thing became immediately clear. This isn't just cooking. This isn't just boiling water on a stove. This is a critical, high-stakes chemical race. You've got sterilisation, isomerisation, protein chemistry, and flavor development, all happening simultaneously in a single vessel. It's basically an incredibly complex gauntlet that this liquid has to survive. And the margin of error here, it is absolutely razor thin. 2%. Here is the brutal truth of industrial brewing. If you fail to evaporate as little as 2% of your wort volume during the 60-minute boil, your finished beer is literally going to smell like a pot of boiled corn. Seriously. That ruinous compound is called DMS, or dimethyl sulfide. It's generated way back on the malt kiln, it survives all the way into your kettle, and only a vigorous, sustained rolling boil will physically drive it away as a vapor. Miss that 2% mark, and boom, you've ruined the entire batch. So you're probably wondering, what exactly is happening inside that boiling kettle to make it so unbelievably demanding? Well, every industrial brewing operation essentially treats wort boiling as a strict checklist. There are 8 non-negotiable chemical and physical objectives that the boil absolutely must accomplish before that raw wort is fit to move on to the yeast and actually become beer. Think of it as this unforgiving quality gate. Let's look at the heavy hitters on this list. Now, what absolutely blew my mind here is the pure chemistry of the hop addition. I mean, we all know hops provide bitterness, right? But just throwing them into hot liquid isn't enough. The bitter resins in hops, they're called alpha acids. They dissolve easily in hot wort, but they are completely unstable. They have to undergo a heat-induced molecular transformation called isomerisation. This is a literal structural rearrangement of the molecules. It locks in and stabilizes that signature bitterness so it persists all the way into your glass. So no heat, no isomerization. No isomerization, no bitterness. It's just a brilliant, direct chemical trigger. And oh man, it gets even better. We're talking about one of the most important chemical reactions in all of food science, the Maillard reaction. Intense heat applied to the rich mixture of malt sugars and amino acids in your wort drives this insanely complex cascade of non-enzymatic browning. And this isn't just about turning the liquid a darker shade of amber. No, this reaction creates entirely new, incredibly complex flavor compounds. It's literally the exact same high-energy chemistry that perfectly browns your bread crust and brilliantly sears a steak, and it's happening right there in the boiling kettle, giving your beer immense depth and character. All right, let's blitz through the rest of this massive checklist because this kettle is working overtime. First up, sterilisation. Raw malt and hops carry microorganisms, so the boil acts as your first fundamental line of defense, just obliterating any living spoilage organisms. Second, enzyme deactivation. Boiling acts as a hard stop, destroying any surviving mash enzymes so they don't invisibly change your beer's sugar profile later on. We already talked about volatile evaporation, driving off that corn-flavored DMS. Then there's protein coagulation. The intense heat denatures malt proteins so they clump together into what's called a hot break, saving your packaged beer from becoming cloudy on the shelf. We've also got wort concentration to hit your target gravity, and finally pH reduction, which cascades into better flavor stability and healthier yeast growth. Miss just one of these, the batch is compromised. But here is where the source material we're looking at reveals a dramatic pivot. We just covered the what, the 8 staggering biochemical objectives happening all at once. But achieving all of that complex chemistry consistently, safely, and at a massive scale across hundreds of brewing cycles, that isn't just a chemistry test anymore. It is a massive industrial engineering problem. And the solutions engineers have come up with over the last century to handle this are nothing short of fascinating. To really understand the scale of this engineering challenge, let's look at where we started, the traditional direct-fired copper kettle. You have a heat source, literally an open flame or firebox, localized right at the bottom. Copper was used because of its amazing heat transfer properties, which is exactly why we still call these vessels coppers today. But because the fire is blasting only the bottom, the fluid dynamics inside are chaotic and sluggish. The recirculation is incredibly poor, really struggling to create the vigorous rolling boil currents you need to mix everything properly. Plus, you constantly risked caramelization and burn marks right on the base. And because of this localized heating, the absolute maximum practical volume you could pull off was around 300 hectoliters. For the booming global beer industry, engineers desperately needed something better. So they evolved the internal heating systems. Moving to steam-driven internal elements allowed for much larger vessels and far more consistent temperatures. And it happened in 3 main steps. First, horizontal internal coils. Definitely better than a direct fire, but the rolling boil currents were still pretty sluggish. Next, they moved to centralized vertical coils, which improved those upward thermal currents to finally get a better rolling boil going. Finally, the real breakthrough: vertical elements capped with a chimney and a spreader plate. This spreader plate disperses the rising, boiling wort across a much wider surface area, forcing vigorous, turbulent recirculation. The catch, though? These internal coils are a total nightmare to clean. Your clean-in-place or CIP systems struggle with blind spots. They foul rapidly, demanding constant labor-intensive cleaning cycles that brewers certainly don't look forward to. So, to solve this cleaning nightmare, engineers completely reimagined the system. Instead of fighting those chaotic, tough-to-clean vertical coils inside the tank just to force a rolling boil, they pulled the heating element entirely out of the vessel. This creates the elegant, modern external Calandria. They circulate the wort through a shell and tube heat exchanger located on the outside. Steam sits inside the shell, while the wort shoots right through the tubes. The wort never touches the steam directly. It is a massive leap forward in both fluid dynamics and sanitary design. And what's really fascinating here is the physics engine driving it. It's called the Thermosyphon effect. This is pure engineering elegance. During the pre-boil, a small pump primes the system. But once boiling actually starts, you bypass the pump completely. Why? Well, because hot liquid rises. The incoming wort enters the external boiler at exactly 100 degrees Celsius. As it passes through those steam-heated tubes, the superheated vapor and wort exiting the top hit about 105 degrees Celsius. That tiny 5-degree temperature differential creates a powerful natural convective loop. The hotter liquid rushes up and back into the kettle, naturally pulling the cooler liquid down into the boiler. It's a completely self-sustaining circulation loop that requires zero mechanical assistance. So the really crucial point here is how many problems this one piece of engineering solves all at once. Because we aren't using a mechanical pump during the actual boil, there is zero mechanical shear tearing apart those fragile protein flocks. You know, the hot break we worked so hard to coagulate earlier? Furthermore, the incredibly turbulent, fast-moving flow inside those external tubes gives the system a massive degree of self-cleaning. The surface fouling is drastically reduced. With the old internal systems, you're constantly scrubbing. But with an external Calandria, a brewery can comfortably push through 8, sometimes even 16 or more back-to-back brews before having to shut down for a cleaning cycle. It's just an absolute marvel of efficiency. And engineers didn't stop there. They took it one step further. By reintroducing that naturally rising wort from the Calandria back into the kettle at a precise tangential angle, basically shooting it along the curve of the outer wall, the kettle itself doubles as a whirlpool. This perfectly uses those rolling boil currents to gather up the solid trub and coagulated proteins right in the center of the vessel. It perfectly combines 2 massive separate process stages into a single vessel, completely eliminating a time-consuming transfer step. All right, let's switch gears for a second, because this brings us to a massive revelation in modern brewing economics: energy recovery. Wort boiling is by far the most energy-intensive stage of the entire brewing process. The thermal load is absolutely staggering. Traditionally, to hit all those chemical targets and drive off the DMS we talked about, brewers had to accept an evaporation rate of around 10% of their total volume. That is a colossal amount of energy literally vanishing into thin air. Today, thanks to the precise fluid dynamics we just discussed, the industry has aggressively driven that number down. A modern system can achieve the exact same chemical checklist with just a 2% evaporation rate, or 4% if they are utilizing advanced energy recovery techniques. And that energy recovery is where the modern kettle becomes a true industrial marvel. The steam that is evaporated off the boiling wort, it's no longer just vented out of a chimney and wasted to the atmosphere. It carries massive, valuable thermal energy. Breweries now capture that evaporated steam and recycle the whole shebang. They use it to generate massive amounts of general hot water for cleaning, or, incredibly, they route it to preheat the incoming raw wort arriving from the lauterton. Think about that for a second. You are literally using the waste heat of your current boil to fund the energy requirements of your next batch. Add in high-grade vessel insulation, and the energy efficiency absolutely skyrockets. But there is a fascinating practical limit to this efficiency: the 4% economic threshold. Now you might be wondering, if 2% evaporation works perfectly well chemically, why would you ever boil at 4%? Why not drop it to 1% or even 0? Well, below 4% evaporation, the sheer volume of steam you are generating is so low that it actually becomes economically unviable to capture and recycle it. The complex infrastructure of heat exchangers and capture pipes simply isn't justified by the tiny amount of steam produced. So this 4% mark establishes a firm, practical lower bound on how aggressively a large-scale brewer can reduce their boil-off while still capturing and utilizing that extremely valuable waste heat. So let's bring it all together. That single 60-minute time frame we started with, it's not just a heating step. It is simultaneously a sterilization chamber, an enzyme kill switch, a volatile evaporation column, an isomerisation reactor for your hops, a protein coagulation vessel, a Maillard reaction flavor laboratory, a precise concentration unit, and a pH control system. All of it running flawlessly in unison. And the vessel where it happens has evolved from a simple, direct-fired copper pot sitting over an open flame into a highly precise, self-recovering thermosyphon marvel of modern industrial physics. People love to look casually at a pint and call it just fermented grain water. But as this explainer shows, it is so much more than that. The sheer industrial gauntlet, the complex fluid dynamics, and the intense, unforgiving chemical checklist that liquid had to survive just to make it into your glass is staggering. You are drinking the result of a century of hard-fought engineering evolution. I hope this completely changes the way you look at the brewing process and maybe gives you a little more appreciation for the intense science happening behind the scenes. So, think back to that massive checklist we covered at the start. Which of the 8 chemical purposes of the boil surprised you the most? Was it the intense heat of the Maillard reaction browning the wort, or the literal shape-shifting of hop isomerization? Think about it next time you pour a glass. Until next time, keep exploring the incredible engineering hidden in the everyday.